Simple harmonic motion, part 2. Here are priming questions. Pause, write them down, and we're going to move on. Here's a Foxtrot comic that relates to the lab that we're doing. You can read through this. You can pause it as I scroll. So pause. And hopefully that gives you a good idea of the equation. If it doesn't, or it also gives you an idea of what you should expect for your graph and what we'll be doing in the lab. And so here's our equation. And this looks like two separate equations, but in actuality, it's simply one equation. I personally memorized the one on the right, but either one will work. And so here we have t squared is equal to 4 pi squared over g times L, or you can also see it as t equals 2 pi root L over g. And the reason why I have it set in both is so that you can see something. For your lab, what you should have noticed is that the period, which is represented by the capital T, and the length had a relationship to each other. As you changed the length, your period also changed. And when you put this into your Excel spreadsheet, what you will find is that it is a curve, which is more difficult for us to be able to analyze. And so we are going to straighten that curve by squaring the period. And when you graph the modified data of t squared versus the length, when you get your slope value, what you're going to be doing is doing your percent error using this as your slope value. And let me do a quick derivation for you so you can see that. Let me just erase this. And so the format that you're going to be thinking about is when you have your t squared versus your length, it's going to be a linear graph. So you're going to see it. If this is your graph, it'll look something like this, where we have our period squared on our y and our length on our x. So in this case, the equation we have is y equals mx plus b. And what we're going to do is we are going to set our intercept, our b, to a 0, so that our equation becomes y equals mx, which tells you, since your t squared is on your y, so that's going to be our t squared over here. Let me use a different color now. So that's going to be our t squared is going to be on our y, and the length is on our x, which means that what is remaining, the m, the slope, is going to be equal to what's in these parentheses, 4 pi squared over g. And so what you're going to be doing is, for your percent error calculation, you will have a slope value from your graph. You also know that we have 4 pi squared over g. This is going to be constant for us because of gravity. And so your percent error, what it should have been equal to is your true value is going to be equal to 4 pi squared divided by 9.8. You can do that calculation. And your percent error is going to be this true value minus what you got from your lab slope divided by the true value times 100. And that's going to be your percent error. There you go. So, equation, graph, and then we can get our percent error. All right, let's move on. Damping. This is going to be another new term. This is the definition, the decreasing amplitude of any oscillating object. And for us, in the real world, anytime you start a motion in object like this, there's going to be damping. And the way you can tell is because over time it will slow down and eventually stop. Now, we can control this damping in many cases, and so I want you to think about, where do you think we would be able to use damping, and why would we want to dampen the motion of an oscillator? We'll talk about that in class. So, a couple of practice problems. If a pendulum makes 42 vibrations in 50.0 seconds, what is its period? Remember, the period is going to be seconds per cycle. So we know we have 42 vibrations in 50 seconds. So it's going to be 50 divided by 42. and that's going to give us 1.2 seconds. The frequency is the opposite of that. It's going to be cycles per second. And so we can do 50 divided by 42, and that's going to give us 0.84 hertz. Now, the other way that we could have solved for this is after we had the period, what you notice here, and what we've talked about in class, is that these are inverses of each other. And so we can say that the frequency is equal to 1 over the period. So we could have done 1 over 1.2, and it'll give us the same answer, 0.84 hertz. So once you have the period, you can calculate the frequency, and vice versa. What is the period of a simple pendulum 64 centimeters long on the Earth? For this, we need to go back to our equation. So we have T is equal to 2 pi square root L over G. And here's where we have to be careful. The length must be in meters. And this G is going to be meters per second squared. So we're going to use 9.8 for that. But with the 64 centimeters, we need to convert that to meters. And 64 centimeters, the way we convert it to meters, cancel out the centimeters. So we have 100 centimeters in 1 meter. So we get 0.64 meters. So when we calculate our period is equal to 2 pi square root 0.64 divided by 9.8. And when you calculate this out, you get 1.6 seconds. Now, you want to build a grandfather clock with a pendulum, a weight on the end of a light cable that has 1.0 seconds between its tick, swing to, and its tock, its swinging fro. How long do you make the cable? Now, for this one, you have to read carefully because in this case, if we have a pendulum, it'll tick on one side, but on the other side, we can consider that to be the tock. And so this is going to be 1 second. And if we're looking at our period, we need to double that time because it takes 1 second to get back. And so we know that our period is now 2 seconds. And once we know that, we can plug it into our equation, which is going to be our T is equal to 2 pi square root L over G. So we have 2 is equal to 2 pi square root L over 9.8. And when you work out this math, you should get your length as 0.99 meters. Do the math yourself. Make sure you can work this out and to check my values. The length of a simple pendulum is 0.72 meters. The pendulum bob, that's going to be the mass at the end of the pendulum, has a mass of 310 grams, and it is released at an angle of 14 degrees to the vertical. With what frequency does it vibrate? In this case, you're given a lot of information, and we have only a limited number of equations. In fact, only one right now for frequency, and that's going to be frequency is equal to 1 over the period. And if we look at this, we don't have enough information seemingly at first, even though we have a lot of information. In this case, we know that our frequency is related to our period, and our period is related to the length of the pendulum. We're given the mass and the angle, but we don't have an equation that works with the mass and the angle, especially with pendulums. In fact, the only equation that we have for pendulums is T is equal to 2 pi square root L over G. And this is the equation we're going to use. In this particular problem, you're given a lot of excess information that you need to sort out so that you don't confuse yourself. So here we have T equals 2 pi square root L over G. And so in this case, to find our frequency, we first need to find our period, and we find our period using this equation. So we have T is equal to 2 pi square root, the length is 0.72 meters over G, 9.8. And from here, we get T is equal to 1.7 seconds. And if we plug it into our equation over here, it's going to be 1 over 1.7, which means our frequency is 0.59 hertz. All right, this is the practice problem that we are going to check in class. So pause it, read through the problem, work it out, find the value of G on this planet, and we still have one more slide. So this is going to go back to the definition of simple harmonic motion. And remember, simple harmonic motion is where the restoring force is directly proportional to the negative displacement, which leads us to our next equation. This is what we call Hooke's law. When we're working with an ideal spring, this is the definition of simple harmonic motion. The restoring force is directly proportional to the negative displacement. Here we have a K. The K is the spring constant. If you think of that, the spring constant is what determines how hard it is to compress or pull a spring. And the X here is the displacement. You can think of it as F is equal to negative KD if you want. It's all the same. And so we have our force in newtons, our X or D, that's going to be in meters, and then our K. Actually, let me show you this derivation. If we isolate our K, and the negative here simply tells you the direction that goes with the definition, many times we can describe this equation as just F is equal to Kx or Kd. If we want to find what the variable K, its units are, all we need to do is move this over, the X over. So we have, if we have newtons is equal to K times X, which is going to be in meters, divide this over, so K is equal to newtons per meter. So the units for your K are newtons over meters, or newtons per meter, and that's the spring constant K.